I'm so happy we're doing Cats and Chats.
Hello, yay, Cats and Chats.
I feel like Cats and Chats also needs a food. It should be like Cats and Chats and snacks or something.
Cats and Chats and a warm cup of water.
Nice. So I was excited about hearing about basically anything you're excited about in math these days.
Oh, what am I excited about in math these days? Something that I've been excited about in math for a long time is playing with notions of relation. And so a lot of math traditionally, in a tradition that goes back maybe 100 or more years, is to base math on functions. And so a function is you have an input space and an output space, or an input set and an output set, and it takes each value as you're given input, it gives you a unique output. Relations are a separate structure which just says we have two spaces and how do they relate? Which things over here relate to things over here? What's really interesting about these to me is that they seem more real to how the world is as it sort of lies in the natural world. So when you think of like what I know Kepler's laws do when they describe the motions of planets, they really just say you take a space of trajectories that the planets could take, and then it selects out, the ones that are real that can be realized according to the laws of the space. Or that when you have something like a circuit component, you have all these currents and potentials that can live across the wires in theory, so that's an entire space. But you select out which ones are compatible with which other ones. And what's nice about this, I guess, is that it's it's not just sort of a predicate on a space. It's not just saying, you have a function from a space to say what is, I don't know, a function to the Booleans or something that says what is true, what is false. When you talk about a relation, you partition this space into various aspects that can be joined together. So it's still got this compositional aspect to it, which also sort of plays very nicely into things like circuits, which are sort of naturally there when we have like little devices. Most of my devices are wireless at the moment, but to be composed.
Neat. Can you say a little bit more about, like in the example of circuits, what that composition looks like?
In the example of circuits, so here we are. Let me grab a wire. Yeah, we do have a wire here somewhere. There's sort of, in some sense, two spaces here: a space of say potentials and currents that live on this end, and a space of potentials and currents that live on this end. And if I grab another wire, so this also describes some sort of relation. And when we connect them, we say, well, we're now constructing a relation between this space over here and this space over here. And it's the one where the values here, so the potential here, say, agrees with the potential here, or the current flowing out here agrees with the current flowing in through here.
And so when you say the space on the two ends, you sort of thinking about that as like the voltage or the potential at that point relates to a potential. So why is that not, I guess like in the case of circuits, I actually do think of that as a function. Like if I set the voltage of one, it'll set the opposite end. Is that not true?
So in the case of something like this, which just has is just a wire that basically transports currents and voltages from one end to another, it is a function, and it's basically the identity function. But let's see if I just take apart all my machines.
Hopefully
here's something that's a multi-port thing, right? You have one port here, but you have all these ports over here. And this is not really a function, because if we think about the current, we might think of this as the input because it's the one that connects to the computer or something. The computer sends signals through here. But if you fix some sort of current here, that doesn't determine the currents that come out through each of these ports. Instead, it just puts a constraint. So if this was, like an idealized thing, and we're just talking about a power board, say, that takes one power outlet and turns into 5 power outlets, then the currents here would just have to sum, the currents drawn by all these things would just have to sum to the thing over here. But if we put in, say, 1 amp through here, we could do 0.5 amps and 0.5 amps, or we could do, well, there are 3, let's say, so 0.5 amps, 0.5 amps and 0 amps, or 001, or, many, many options.
So that's how it makes a relation instead of just like a function between stuff. That's
more
cool.
a relation instead of a function.
Do you have other examples of like, when you first said function, I was imagining like a function that takes sheep and matches them to people who own them or something like that. Do you have any like social type examples or like higher level examples that you think about?
So there's one relation that comes up is that sometimes when I say, I don't know, my grandmother, something, it feels like a function because it feels like I'm referring to an actual person. And often there's enough context to actually say, you take me and then you run the grandmother function and you take out a grandmother. But I have 2 grandmothers. And so that's actually a relation but we have these other, I guess, linguistic contextual constructs I could say like my paternal grandmother and my maternal grandmother, and that would turn it into a grandmother function from people to people. But as it stands, grandmother is really just a relation.
That's neat. And then like many relations can sort of constrain each other. Like if you say my grandmother, I'm like, well, now I have this relation that gives me sort of 2 options. But maybe we've been talking about, your mother's side of the family, and so I can constrain it further or something like that.
And so another sort of more complicated relation that isn't just sort of 1 to 2 is like a friend, like my friend or my friends. Friend of is a very relational thing and not a functional thing at all.
That's also, I don't know, this is making me think of like when I say, sometimes I'll talk to someone, right, who doesn't know someone, I'll just be like, my friend and I went to dinner last Friday. And in a way, like they're not operating perhaps on a specific person, but on sort of like, I don't know, something else.
Right. I think that's really interesting, is all I have to say. Somehow our mathematics is often built to only handle functions, but clearly we can handle relations very well as we reason about them and as we represent the world, because a lot of the primitive concepts of the way we interpret the world are relational.
Neat. So can you say more about like how the cats fit into the relational world?
Yeah, that's a great question. So I find this really interesting. Category theory is built on classical category theory is built on the category of sets and functions. So we talk about enriching categories are sort of enriched over that category. There's still working in the world of categories, but there's something else you can talk about in sort of the category of sets and functions, which is the 2 category or locally persettle category of sets and then relations, and then implication or inclusion of relations. So if what that means is, say we have a relation, say best friend, or best friends, that's included in friends. And so this is a 2 categorical structure because we have those 3 levels of things, objects, morphisms, and so those implications as 2 cells.
So that's like there's a hom from like people to people that's best friends. Also, I like that there's like a Mindy Kaling quote, like best friend is a tier, not a person, which is well here. So you have this tier of best friend morphism, and then a best friend morphism, and an inclusion, which says every best friend is also a friend.
Right. And it turns out that these 2 categories can each be built from each other. So you have the 2 category of relations and the category of functions. And so one way of thinking about a relation is, I sort of alluded to earlier. It's a relation from a set A to a set B is the same as either a subset of A times B, or the same as a function from A times B to a classifier 2. So that's one way of taking, starting with the category sets and building the 2 category of relations. But equally, you can go the other way. So functions are just special types of relations. And they have two conditions. One, a relation says, given, you can think of a relation as a function from a set to the power set of a second set. So a relation from A to B is a function from A to the subsets of B.
So like I get mapped to the subset of all people who are my friends or something like that.
Right. But then the functions are the ones that send everything in the input to a singleton set on the output. So we say that first functions are total relations because they're defined, or that they send everything on every input to something, and that they're deterministic because if you give it an input, it goes to a unique output. And it turns out that these conditions are the same as the conditions for an adjunction in a two category of relations.
Whoa.
Yeah, it's
Is there like a
really
theorem
cool.
statement in there?
There's a theorem statement that says, so in any two category, we can take the category of objects and left adjoints. And if we do that in the two category of relations, we get the category of sets and functions.
Cool. So in a way, like, yeah, I mean, there's a way in which functions are like special relations, but this I feel like makes it even better or something. I don't have words for why, but.
So what's really cool here is that the data is really equivalent. So you can imagine we sort of based a lot of our work on sets and functions, but because it's equivalent, you can imagine doing all that instead with relations, and anything you can say with functions, you can do some magical transforms that are non-trivial, but unpack everything and then repack everything, and just base all of mathematics on the bicategory of relations.
Neat. I think I don't quite understand why they're equivalent yet.
That's a really good question, a really good thing to examine.
Or like, it seems, I guess I would have thought that like relations are more powerful, that there are things I can do in a relational world that would not translate back into function world.
That's a great intuition. It sounds like relations are more expressive because every function is naturally a relation, and functions are a special case of relation. It reminds me of the Church-Turing thesis, which roughly is the statement that there's this notion of universal language for computation, or universal programming language, or model of computation, and that we get very quickly to sufficiently complex languages that are capable of expressing everything else, or everything, and the Church-Turing thesis, I guess, is that is the limit of what the notion of computation is. But to be more specific, then, like, you have like the lambda calculus or the Turing machine, and these are very different formalisms for computation. But it turns out you can model Turing machines of the lambda calculus and the lambda calculus within Turing machines, and so they describe exactly the same world of computable functions. And it seems to me sometimes a similar thing goes on with a lot of mathematics, in that it's easy, you make languages that are powerful and expressive, and once it gets to a certain point, and it's not too hard to get to that point, you can start to express other formalisms inside that formalism. So we just spoke about how you can express what a relation is inside the world of sets and functions, as I guess another way of saying it, which captures the notion of composition, is that relations are jointly monic spans in the category of sets and functions. And then the question becomes, well, if I think everything is the same, like everything can express everything else, why choose one language over the other? Or if we already have the language of sets and functions and we're so good at using it, why would we want to move to investigate another essentially equivalent language? And here I think a bit about like the Sapir-Whorf hypothesis, or like linguistic determinism. And just, more broadly, the way that language shapes thought, and that language is a tool for expressing things, or when you have, say, programming languages or mathematics, which is kind of gets this life of its own outside just thought, because you can code it and you can create machines that formally execute it and so on. We're talking about sort of the ergonomics of our tools, like what they're naturally suited to describing, and therefore, what actions they're naturally suited to taking. And so an interesting example of, say, something like linguistic determinism is there are many languages around the world which use cardinal direction instead of relative direction. So instead of left and right, you say words like north, west, east, south, in describing, say, the relationship between how these two objects are juxtaposed with each other. That's an interesting thing to do. So one way that helps shape thought is that to even communicate in a context like that, you always need to be aware of the cardinal directions. And I'm certainly not. If you take me, if I'm wandering through a house and then you ask, like, which way is north, most of the time I won't know. So it's cool that just having the language makes you aware of certain things in the world around you.
Yeah. I heard this cool thing where, like, I don't know if it was a languages where use the cardinal direction, but they actually think of themselves, instead of like an agent with my eyes, they think of it as like a dot in a map moving or something. It like changes the way you think and interact.
There's another fun thing in experiments that have been done. I'm not sure how universal they are, but in naturally, English speakers say, often order things from left to right. So if you, like, I don't know, have these sequences of a person aging over time, you order them from left to right. But in some instances, it's more when you have these different languages shaping your thought, it's more natural to order them from, say, east to west, because that's the way that time passes.
I heard about this. Yeah, it was very cool.
Really cool. So in terms of how this relates to, like, functions and relations, I'm really interested in the different ergonomics of functions and relations. So I said earlier that somehow I think of a lot of sort of more physical things are more relational in their nature. And you can, electrical engineering has proceeded very, very well with functions as the base structure. And these things and many other things are very, very impressive. So it's certainly possible to think very deeply about these objects with functions. But nonetheless, it seems to me that it's just really lovely to think of them as relations, to think of things like, you have formalism that have been developed like circuit diagrams, but how do we understand a circuit diagram, especially when we talk about, like, what it means to draw, like, a junction in circuits, which relates to this power board example or this multi-adaptive example, right? If we want to give semantics for circuits, if we want to say, if we want to draw pictures and say, what does this picture mean? It's really difficult to say what it means as a function, where it's really easy to say what it means as a relation. And I think that's partly why circuit diagrams are so important for doing things like electrical engineering.
I wanted to ask, like, do you have an example of, like, a particular mathematical formalism that's taken more the relational perspective, and, like, has it changed how you think about things, or given you different ergonomics, or made it easier to state or do certain things with that?
One thing, well, when you express what is okay, I've just got items in front of me. What this thing is, like, and as an inventory in like a shop or something, then it will have a name, but it will also have, like, a size and a weight and a price. And this can be represented as some sort of relation that, you have this giant space of possible weights and prices and names and so on. And this will select out each item for sale will be a particular one of those element of that set. And so you'll have a relation there. And so where I'm getting to in this example is there's a really lovely visual way to think about certain database queries where you want to select, things with a certain price, or a price that is equal to, say, the sum of money in, I don't know, a person's wallet or something like that. And so what you have visually is these multi-arity relations. So often you represent functions as just a box with an input and an output, but you can imagine relations represented as some sort of, say, circle, and it has all these attributes coming off it. And then when you want to say that two things are equal to another, just like I want to say that the current here is equal to the current here, in this more general setting, I want to say the price of this item is equal to the amount of money that is able to be offered by this customer or something. And you can sort of visually just connect them together, but that represents the identification of those two values.
And I can do even more complex things, like if we wanted to jointly purchase something, I could add in the amount I also have, or something as a sum or something like that. Or if we only wanted to buy fruits, I could like specify that the thing is a fruit.
Right.
Add these constraints.
Exactly. And if you didn't really care about a value, you can just like let that y terminate or go and forget about that. And so this expresses an important fragment of logic called regular logic, where you're allowed to say things like and also you're allowed to existential quantify and say, well, as long as a value there exists, we don't really care what it is.
I have a sense that there are math words hidden in everything you've said recently. Do you want to say those math words?
Okay, how would I say those math words?
Or even just the keywords if you want.
The keywords are, there's a lovely graphical way of thinking about these things called the I don't know, monodal category cospan or the operad cospan that talks about all the gluings you can do, which are very simple. They're just, how can you connect wires together? It's what it describes, which is also like, how can you decide when things are equal? So that's that aspect of it. And so that provides the visual syntax for talking about relations in a really rich way. And then I guess something deeper that's going on is similar to what we were talking about with how using functions, you can build this sort of two-category relations, and using the two-category relations, you can take the adjunctions in and get back your category of functions. What's really going on there is nothing very specific to sets and relations, but specific to this fragment of logic known as regular logic, which again has this and the existential quantifier and a truth value, like a value true. And so it turns out that the category of sets and functions is a regular category, which in this case means it can express that logic, and you express it using finite limits and image factorizations. And then from these things, whenever you have a regular category, you can construct this, what I might call a regular bicategory or a relational bicategory from it. And that's this sort of nice visual thing where you can plug things together, and it has this cospan syntax. And anytime you have one of them, you can go back to your regular category. So there's a lovely sort of equivalence of certain categories with certain bicategories that express this logic. But what I really like is, I guess, the way that you transform, sometimes working with like limits is a really strange way to express like I don't know, and but there's something really lovely in the bicategory picture of just expressing and or equality by like plugging things together.
And I guess that's sort of this like ergonomics maybe that the relational point of view gives you, is you're like, this thing that is so natural, now also natural to express.
And so I think some of your work is another example, but there are subtleties to make it fit into this picture, but something like the way that you can glue all these epidemiological or models, these either stock and flow models or SIR models together, again, you have this visual logic of just gluing things together in this relational framework, which is really hard to express in a functional framework. But allows really clear collaboration with, like, it's just very easy to interpret. I have this picture of the puzzle, you have this picture of the puzzle, and then we just glue them together, and suddenly we have like a model of I don't know, disease dynamics between different populations.
Neat. I guess I have two questions. One question I have is, do you want to talk about decorated co-spans? Which the answer, I feel like we've already talked a lot, so up here. So that was my first question. And then I was also curious, like, I don't know, if tomorrow someone's like, wow, Brendan, you have 6 months to, or I don't know, some amount of time to do whatever math you want to do. Like, is there a thing you'd be interested in tackling, or like, what are you sort of excited about upcoming, that sort of?
One thing I'll say about decorated co-spans, without getting into technical details, is, again, it fits in this framework of trying to look at, in particular, what languages exist out there that seem, to be invented outside the existing formal frameworks of language, whether it be natural language or sort of mathematical language. And in some ways, you view all these people invent diagram languages over and over, and they often do it heuristically. But there's really some insight in the invention of that language. And as it develops in a particular field, it often becomes more and more formal. So it really, every symbol, every diagram or something is constructed according to a precise grammar, and every symbol has a precise meaning, and the construction, the meaning of the diagram is a result of the meaning of the symbols, the components, whatever, and the grammar that's used to connect it. And what's really exciting there to me is to actually make good on that promise of formal language by providing new mathematical structures, so that we can execute them computationally, or just really understand and have clarity about what's going on.
I was going to say, you had mentioned the sort of epidemiology models and like the composition of these, the gluing together of these like stock and flow diagrams or Petri net models is all sort of based in this common decorated co-span language. Yeah.
And then to me, it gets at almost a radically different worldview on like what our primitives are for interpreting the world, because it is relational in this, not just in the technical sense, but in the sense of talking about how things relate to each other, and making that as the first class primitive. A lot of these multi-part things that with multiple aspects that we kind of merge together into a larger picture. And there's this contrast between that and I think the functional viewpoint for me, which is very much about sort of cause and effect. It's very much about if I do this, then this unique thing will happen, which is again a very powerful way of thinking. But I love having both of those available,
and that they're somehow equivalent or
right.
Pass between them.
That in the end they're all sort of describing the ways of navigating the real world around us. And then you had another question, which was, what would I do? I have lots of half ideas. I'm not sure how well any of them are thought through. One idea that I was playing with yesterday was inspired by something Brandon was talking about earlier this week on growth and deconstructions, and viewing them as so growth and deconstruction gives a correspondence between some sort of fibered structure. So you have a base category, and let me give a more precise example. So say you have a set of like types, like things like people, or maybe an ontology for a database. So there are people and there are animals, and they have relationships like, animals like certain people. And so you can write that down, and then a C-set or a co-presheaf on that category, that database schema, says, okay, here are some actual people. There's me and there's you. And there are some actual animals, and they have all these relationships. And so that sort of uses the category as a schema to index sets of what's going on. But you can also construct this world that lives over your sort of type system and says, well, here are all our people, and they have these relationships. And then you can have this functor that says, well, Sophie is a person, and I don't know, Milo is a dog, and so on. So what allows you to do this is in part this way of saying, well, we have our symbols here like people and animals, and they're interpreted as sets of actual concrete sets of the people and the animals. And how you really understand what they mean is that you have a universal vibration over that, where you can map like the idea of people to the set of people, but you need to actually say what that set means. And so there's another thing over here. The punchline is that it's really interesting to me to play around with this notion of like universal object, where what is fibered, like that sort of vibration gives meaning to all your symbols down here. So you write the category of sets, but it's really given meaning by saying the lax category from undercategory from one picks out, it sort of gives you all these things where it says one is an element, like it picks out all the elements of your set. So it gives you a new object for every element of your set, basically. But instead of giving that meaning to sets, you can talk about giving, say, subsets as the meanings of sets. And there's this puzzle playing around with these correspondences between, say, in regular logic and these logical ways of presenting constructions versus looking at, say, I said regular category, so the regular category that lives over it. So they're often called things like hyperdoctrines. So you have a regular hyperdoctrine, which takes a bunch of like types and some very, very simple ways in which they relate, and then gives you all the functor gives you all the terms of that type. So like the poset of terms of that type and how they imply each other. And then from that hyperdoctrine, you can construct, it gives you a way of presenting a regular category. So an actual like complete object where it's all bundled together.
And that's the sort of thing I can do like gluings with.
Yeah.
So I think what I've heard is you've sort of like, here's a really cool, thing that Brandon presented, but it feels very like function-y. Like, what would it mean to sort of take that story and make it more relation-y or translate into the relational world?
That is a great question, but that question is hard.
Okay, so what are sorry,
so
then I think
I wouldn't want to tackle that in the next 6 months, or like not the whole question.
Yeah.
And my question here is simply, there are certain constructions there that look sort of growth and so there's this very well-known construction called the growth and deconstruction, or the category of elements, but that and in one of these categories of elements, your objects are like a type from here, and then an element of the image of that type over there, right? And that's what those things are, what become the objects in the thing that's fibered over your types. With these hyperdoctrine constructions, you do the same thing, but the morphisms look quite different. The morphisms have this much more logical nature. But I'm almost sure that this is actually well understood by someone else, just not me. So it's not really a research problem. But I want to understand how that could be mediated by switching out your notion of universe object. And that sounds fun to me because sometimes like I'm curious about like what does a set really mean, or what does a number really mean, and whether you can add richness to that notion. A related thing that comes from, say, thinking about some of David's stuff on polynomial functors, and how in that world, you often think, when you have, so you have the natural numbers, but we categorify that as say, the category of finite sets. And from the world of natural numbers, you often think, well, 2 plus 3 is equal to 5.
Mm-hmm.
But sometimes you want to say, that 2 plus 3 is really just 2 plus 3. You have two things and you have three things, and they're not the same sort of thing. Like I don't know, I hope I'm not escaping too far from the model when I say like 2 chairs plus one table plus 4 chairs is not the same as like 5 things.
Mm-hmm.
And you kind of want to retain that sum. And so what you can do but what's interesting is that in the world of polynomial functors, right, you take in the category of sets, 2 coproduct 3 is 5, or that is isomorphic to 5. But in the category of polynomial functors, you replace that with a representable of 2 and the representable of 3. And when you take the coproduct, it's really just y squared plus y cubed. It remains its own thing, its own right, and that has a certain relationship to the notion of 5, which is the representative of 5, y to the 5. But they're distinct things. That seems to me similar to this notion of playing with this universe object, because you have a set of symbols down here, like 2 and 3 and 5 and whatever, but you have this way of mediating what they mean by fibering the meaning over them.
Cool. That sounds fun.
Yeah.
Is there anything else you wanted to talk about in general?
I think I'm good. This was fun.
This is really fun. Thank you so much, Brendan, for chatting and catting.
Yay! This was really fun too. I'm glad to have done my first cats and chats. I hope there are many more, and I hope you host many more.
You too.